Now that we've discussed AVL trees, we can talk about another slightly more complicated extension of the binary search tree that's also self-balancing, called the red-black tree. I've drawn an example of a red-black tree here, and I'll use it to help describe the different properties of red-black trees. So the first property of a red-black tree is that all nodes must be either red or black. So here I'm drawing black nodes as blue because black wouldn't show up on a black background, and I'm showing red as this pinkish red color. So my blue nodes are 30, 15, 70, 10, 20, 85, 50, and 65. And my red nodes are 5, 60, 80, 90, 40, and 55. The root must be black. So here 30 is the root and it's black. If a node is red, all of its children must be black. So in other words, I can't have a red node that has any red children. So here I see my red nodes are 5, which doesn't have any children, 60, which has 2 children, both of which are blue, 80, 90, 40, and 55 don't have any children. For every node U, every possible path from U to a null reference must have the same number of black nodes. So for each node, any possible way I can get to a null reference must have the same number of black nodes. So a null reference is just an empty child. So for example, here, 10 has a null reference to the right, 5 has 2 null references, left and right, 20 has 2 null references. So I'll just go ahead and fill these all out. So all of my leaves have 2 null references, a left and a right. It's something that could have been a child but is currently null. And then elsewhere in the tree, so 20 was also a leaf. 10 had a null right child, and it looks like nothing else in the tree has any null children that I haven't already marked. So other than leaves, the only one that had a null child was 10, which had a null right child. So yeah, so for every node, every single possible path from that node to a null reference must have the same number of black nodes. So here, 5 has no black nodes on the path to a null reference or to this other null reference. So it has 0 to this one, 0 to this one, success. It has 0 to every possible path to a null reference. 10 has itself, so it has 1 black node on the path from itself to this null reference, 1 black node on its path to this null reference, and 1 black node on its path to this null reference. 20 has 1 black node to either of its null references. 15 has 1, 2 black nodes to either of these 2 null references. 15 has 1, 2 black nodes to this null reference, and it has 1, 2 black nodes to either of these 2 null references. And I could keep doing this with every single node in the tree. So a more complicated one, I'll just zoom out to the root. The root has 1, 2, 3 black nodes to either of these 2. 1, 2, 3 to this one. 1, 2, 3 to either of these 2. 1, 2, 3 to either of these 4. 1, 2, 3 to either of these 2. 1, 2, 3 to either of these 4. So every single node in the tree, I should be able to take any arbitrary path to get to a null reference, and I should hit the exact same number of black nodes for every single one of those paths that I could take from a given node. That's a little bit complicated, but hopefully it makes sense. And I didn't mark this as a property because it's not really a property, it's more of a definition. But all of these null references, these children that don't actually exist, are black. And the reason for this, if I have a red leaf, both of its children should be black. So these are all the properties that a red-black tree, which is a special type of binary search tree, must have.